So here goes. Last week we ended up by describing a method which would convert a two-dimensional image to a vector. And I don't want to spend too much time going over that. I want to start a new topic today, which is the distance classifier. Now, this applies to distances between vectors, and vectors represent patterns. And we're going to make the assumption that the closer the vectors are, the more similar the patterns are going to be. And so it can be used to classify real-world data. Now, that's an assumption that the physical distance in pattern space is the same as perceptual distance, which is the similarity you and I make when seeing patterns.
You haven't shared your screen.
I haven't shared my screen.
You got this desktop.
Right, have you got my screen, I hope? Right, let's...
Wait, give me a second. No, I don't see a screen. No, it shows with sharing. Can someone confirm that you could see the shared screen? I cannot.
Yeah, I can see it.
Okay, thank you.
Right, a vector in two dimensions. We can plot it out in two-dimensional space as a graph. The axes of the graph, the vertical axis is dimension 1, and the horizontal is dimension 2. And if I take a vector A, which is two-dimensional vector A1 and A2, that is going to be a point in two-dimensional space. The vertical coordinate is A1, the first dimension. The horizontal coordinate is A2, which is the second dimension. And the vector, let's change my pen color. The vector is the line from the origin to the vector point. So what started off as a pattern is now becoming a point in vector space. Now, unfortunately, we can only draw two dimensions. Well, with a bit of ingenuity, I might go to 3D, but beyond 3D, we can't visualize on a graph space. So the ideas can be shown and the problems identified in two dimensions, and they are the problems which might occur in multi-dimensional space. Now, two dimensions we can draw, 3 dimensions we can imagine, 4 dimensions is beyond imagination, but mathematically okay. And of course, as we increase dimensions, it could be 40 dimensions, 400, 4,000, even with images, 4 million dimensions. So the possibility of seeing what's happening in that dimensional space is not possible, but we can apply the mathematics and the ideas based on a simple two-dimensional image. So now let's have a look at distance in pattern space. Whoops, there's a pen. Let's take dimension 1 and dimension 2. And let's take two patterns, A1, A equals A1, A2, and B equals B1, B2. And for pattern A, or vector A, there's the vector point. This is going to be coordinate A1. This is going to be coordinate A2. And for B, that's pattern B, we're going to have B1, the first dimension, and B2, the second dimension. Now, the distance between A and B, the physical distance in two-dimensional space, is the line, whoops, let's try to draw it a little bit better than that, It is going to be the line between A and B. So that is the distance D. Now, simple piece of
I
geometry.
think the screen is switched. We can see your webcam and not the computer screen. It just happened 2 seconds ago.
Oh, how on earth did that happen?
You can just click on the whiteboard thing on the right-hand side.
The whiteboard thing, right? Has that brought it back?
No, not yet.
Oh,
Connor, you
No,
just
you can literally click on it yourself. It shows on your bottom right-hand screen.
bottom right-hand screen.
No, I'm talking about the student.
Oh, okay.
Sorry, right.
It's showing for
It's
me.
back now. I can see it. I can see
Good.
your whiteboard now.
Sorry
I don't
about
know what
that.
that's.
Right, that is the distance between vectors A and B. And a simple piece of geometry. This distance here is going to be A1 minus B1. And this distance here is going to be B2 minus A2. And I'm sure you know from Pythagoras' theorem that the distance D is going to be equal to A1 minus B1 squared plus B2 minus A2 squared, and the whole thing is square rooted. And that is the Euclidean or true distance. Right. Now, in 3 dimensions, let's take A equals A1, A2, A3, and B equals B1, B2, B3. Now, you can use geometry in 3 dimensions, but I won't go. Something you can try on your own, but I'll give you the result. The distance D in 3 dimensions is going to be A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 all squared. Now, in the previous distance, I wrote down B2 minus A2, whereas the first term was A1 minus B1. The order of the elements within the brackets does not matter because you are squaring it. So in the general case, I can have A1 minus B1 or B1 minus A1. Squaring them gives the same result. And of course, there is the square root of that. So that is a distance calculation in 3D. Let's now take n dimensions. And in n dimensions, I think by mathematical induction, you can see we are simply adding each dimension the difference between the elements squared. So D, and I'll use subscript E because it is Euclidean distance. There are other distances we will look at. DE in n dimensions is going to be equal to the summation. Here's your summation in the 3D case. It is going to be AI minus BI all squared square root. And that distance can be calculated for any I. 3 dimensions, 30 dimensions, 300. We've got a mathematical way of calculating distance. Okay, so there's a distance formula for multidimensional vectors. Now, let's take a very simple case of binary patterns. That is 1 bit per pixel. And let's take the term AI minus BI squared. Now, AI and BI are going to be 0 and 1 binary. Now, if I want to look at this squaring operation, if A is either 1 or 0 and B is either 1 or 0, that is going to be equal to the mod of AI minus BI. To check, A is 0, B is 1. This term is going to be 1 because 0 minus 1 is minus 1, squared is 1. Mod 0 minus 1 is 1. And you can check out for the other three values, A is 1, B is 0, A is 0, B is 1, and A is 1, B is 1. You will find that that squaring is equal to a modulus. And interestingly, that is also equal to a logical operation. Now, can anybody spot the logical operation that the modulus represents? Well, it's exactly the same as AI minus, AI exclusive OR BI. And again, put in the values of A 0, 0, 0, 1, 1, 0, 1, 1. You will find that the squared term is equal to a XOR operation. So you've now got a hardware system, a very simple hardware system, which will measure the distance between binary patterns. And if I take an array, which is pattern A, and an array which is pattern B, if I pass them through a single XOR gate, and feed that to a counter, then what comes out is the distance. So year one logic, we can produce a very simple circuit that can do pattern classification. So to give an example, if I want the Hamming distance between two patterns, and there is a reference pattern A, and here is a reference pattern B. And let's have a slightly distorted vertical bar. These will go to 9-element binary vectors. So for A, to write the equation out, A, let's assume white is 0 and the cross is 1. A is going to be scanning from the origin. It is going to be 0, 1, 0, 0, 1, 0, 0, 1, 0. There are my 9 elements, so D is now 9. And B is going to be 0, 1, 0, 0, 1, 0. Again, they're not numbers, they are vectors. 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. And if I exclusive OR these two bit by bit, no, 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 yes, yes. The distance will be 2. And this is a Euclidean distance, but in binary patterns, it's also known as the Hamming distance. So, how does the distance classifier work? I think I'll carry on with the whiteboard. It's easier than the PowerPoint slides. So the distance classifier for two classes. Let's have a situation where we've got a pattern class. I'll draw this as a cluster of points, and the typical one in the middle would be A, and a second class, and a typical pattern within that class would be B. And if we look at this system, any pattern within the black set is going to be closer to A than B. Any pattern in the red set is going to be closer to A than B. And in fact, there will be a decision line where the classification changes over. All this side would be A and all this side would be B, according to nearest neighbor, according to distance. Now that decision surface can be calculated more accurately, again taking a two-dimensional model. This is dimension 1 and dimension 2. If I take the single pattern A, which represents the class A, and let's keep the color the same, and the reference pattern B, distances or contours of equidistance around A will be circles. So that's distance 1, that's the distance 2. Let's draw a third one. And around B, we will have contours of equidistance 1, 2, and 3. And if I've drawn that accurately, so it's 1, 2, and 3, the point of equidistance between A and B at distance 3 will be the outer circle. It will be that point there. Let's in fact change the color. Let's put it in as blue. And that would be there. And if I'd drawn all the contours, you would find a line which passes through there. That's the decision surface. Now take away the contours. We've got pattern A, we've got pattern B. Let's keep that red. Oh, rubber. The decision surface is going to be, first of all, take the line joining the reference patterns. A's gone. Why did that go? Never mind. Put it there. And the decision surface, blue, is going to be the line that passes through the midpoint, mid-distance, and at right angles to that line. So that would be the decision surface. This would be the class A area. This would be the class B area. Right. Let's take an example now. In 2 dimensions, examples are pretty trivial, but let's take a classifier that's going to replace exams. And for each of you, I'm going to measure the hours studied and the hours on social media, say. So our 2 dimensions, whoops, come back. Our 2 dimensions are going to be hours studied and this is hours play, if you like. And what we're trying to do is to predict whether you pass your exams by these 2 measurements. So let's take, I haven't got any participants there, but let's take one of you, a random person, person A, spends lots of time studying, spends very little time playing. And then there's a type of person like me down here. Yes, I don't do much studying, I do a lot of playing. And for the whole class, let's assume we've got a distribution, these points. So these are all the good students, And these are all the students who are not going to pass the exams. They're enjoying themselves, but that will not go on forever. So we've got our cluster B there. Now, take a reference pattern from all the A's, and we can take last year's students as the training set. Remember, this is a learning system from last year. We take the performance of last year's students, and so I've got data, and I know whether they passed or failed. So let's average all the black patterns out to give me a typical pattern as the reference pattern. So if I now remove those, and we just have the one training pattern for the A class, and removing these patterns, we have the one pattern for the B class. Those are our reference patterns. Now, I'll take one of you as a test data. You weren't in last year's set, so you are new data. And supposing I have person, whoops, color change. Supposing one of you is there. How do we classify that? Well, we measure by the equations we've already developed. That will be distance AX, and we will be measuring distance DBX. And X belongs to A if DAX is less than DBX, else X belongs to class B. So that is a classification. And if you look up on the web distance classifiers, it appears to be a very simple process. You have reference patterns, you have unknown patterns, you find the distance of the unknown pattern to the reference patterns, find the closest reference pattern. What class is it? That becomes the class of the unknown. It seems to work, but
John,
yes?
for this, do you have to have two distinct like clusters of data, or can it work if it's a bit more ambiguous?
You're making the assumption that the physical distance, the Euclidean distance, matches perceptual distance. That isn't always going to be the case. That's a good point. The system isn't always going to work. And in fact, going on to my next topic, but oops. Supposing we have this situation. Class A and class A is going to be a series of points there, well defined. And supposing I have another class B. If I were to average these points out and take one pattern per class, that one, and I take that one as the average of all those, we know the decision surface is at right angles to the midpoint between the two reference patterns. That would be our decision surface. And the decision surface would classify this as being A, and this as being, I haven't written A on there, have I? That's class A, and that is class B. This would be defined as class B. And of course, all the patterns in this region are going to be closer to B. In fact, we can shade that area in. These are going to be errors. And this is a well-known problem which occurs in a lot of applications, including neural networks. This is a case of linear inseparability. It means that we cannot use a linear surface to separate the two classes. Now you can see the problem in 2 dimensions. You could possibly see the problem in 3 dimensions. But if we go to 4 dimensions, 5, 6, 7, 100, 1,000, 10,000 dimensions, you cannot detect by looking at the data sets, the training data sets, whether this linear separability occurs or not. So the system won't work with this linear inseparability with a single reference pattern. So next case is solution, more reference patterns. And again, taking the same data set, this is going to be dimension 1. Still only 2 dimensions. There was my set there. That was A. And my set B was down there. Yes, that will do. And I will take one reference pattern from the B set, but I will take a range of patterns from the A. Let's have that one, and that one. Right. Now we know the decision surface is the point of equidistance between reference patterns from A and B, but it will always look at the nearest reference. B, we have no choice. There's only one reference pattern. But for class A, if I'm coming in from this region, the 2 nearest patterns will be the B and this A pattern. And the decision surface will come in at right angles to the line joining these 2. So if I'd drawn the dotted line in there, that's the right angle there. And this becomes the decision surface. But let's take it a little bit out there. As we move through this pattern space, moving up, this at some point will not be the closest A pattern. This pattern will take over. We will then have a decision surface, which will be the midpoint between this and this. And as I move out here, this pattern takes over. And we end up with a decision surface like that. And what this gives us as is a piecewise linear surface. And it will solve the problem. Test pattern comes in there. And in using it, you don't have to draw the pattern space diagrams. You simply take the test vector and find its distance between all the reference patterns. So you find a distance there, D1, you find D2, you find D3, and you calculate D4. And so we'd have 4 distances, D1, D2, D3, and D4. And we find the smallest. And the minimum D, looking at the diagram, it will be D1. What class is D1? D1 is a test pattern, therefore belongs to A. So that is possibly a solution for linear separability. But in practice, we can't test for linear separability. We've got data. Imagine these are 10, 15 dimensions. Instead of finding the average pattern, which might average out and give a linear surface, which will not solve the problem, we want a piecewise surface. We need more reference patterns. So I can't tell you how many we need because I cannot see the potential linear separability for any given problem. But normally one would, if one's using a classifier like this, increase the number of patterns, reference patterns for each class from 1 to maybe 10, 100, maybe 1,000. Use as many patterns as you have in the training set to set up these piecewise linear surfaces. Now that explains this linear separability in 2 dimensions, why when using a distance classifier on higher dimensions, you sometimes get the solution, the wrong answer. Now the distance classifier, simple concept, it doesn't tell you when the system fails, and I think the failures are more important to understand than when the system works. And so that gives an explanation in 2 dimensions what might happen in multi-dimensional space. Right, let's have an example. Let's have class A reference patterns. A1 equals 5, 3, 6, 2, 4. A2 is going to be 4, 2, 3, 4, 5. And for class B, B1 can be 1, 6, 4, 4, 1, and B2 is going to be 2, 5, 3, 3, 2. Now this is an example I'm making up on the spot, so I hope it works. So those are my reference patterns. Now a test pattern comes along. And let's have a test pattern. Let's call it X equals, well, I don't know, what shall we have? 3, 4, 2, 5, 3. Now, classify pattern X according to these reference patterns using the distance classifier. Now, the distances. A1x is going to be, I can keep on this. Right, A1x is going to be the square root of the square of the difference between x1 and a1, which is going to be 5 minus 3 squared, plus 3 minus 4 squared, and again it doesn't matter the order because we're squaring the operation, plus 6 minus 2 squared, plus 2 minus 5, whoops, mistake there, oh, carrying on underneath, there's a bit more, plus the last one, 4 minus 3 squared. And working that out, it is going to be 5 minus 3 is going to be 2 squared is 4, plus 3 minus 4 is minus 1, squared is 1, plus 6 minus 2 is 4, 4 squared is 16, plus 2 minus 5 is 3, 3 squared is 9, and plus 1. And it is the square root of that, which is the square root of 16, 20, 21, 30, 31. Root 31 is the Euclidean distance of A the test pattern X with A1. Now, to complete the calculation, I'll leave you to do this in your own time. Find the distance X A2, X B2, and X B3. You will end up with 4 distances. Find the minimum distance. Whoops. Help. Where's it gone? Oh. Nope. Come back. I've lost my whiteboard screen. It's there somewhere.
Look,
Oh,
what you drew? You drew like this,
oh, you were so good, Tatiana.
and just gradually go
Ah.
up and increase.
Now stay where you are. Right, we're back to the calculation. A1x was root 32. Find the other 4. Find the minimum distance. Then classify x according to which class the minimum distance, which pattern class the minimum distance is closest to. Now, a tip. You don't need the square root operation. It's only a single calculation, but it's not necessary because this is a linear function. If the square root is closest, the square will be closest. The normal number will be closest. So root 31, root 14, root 8 is the same as 31, 14, 8. You can still get the classification according to the nearest distance with the without using the square root. So that's one piece of calculation that you don't have to bother with. Right. 3-class problem. Again, I can only show the behavior in 2 dimensions. I can only draw 2 dimensions. This is dimension 1, and this is dimension 2. And supposing I have class A, let's have class B, and let's have class C. There's 3 different data clusters in 2-dimensional space. The decision surface, first of all, coming in from the bottom left. This label that. That's going to be C. The decision surface is going to be between A and C. It is going to be there. The decision surface between A and B is going to come in there. The decision surface between B and C is going to come in there. And they will most probably all meet at the same point. So that would be the decision surface. And again, we can classify an unknown pattern. Supposing the pattern X is coming in there, that's a test pattern. By inspection, clearly, DAX is going to be smaller than DBX, smaller than DCX. And so we can extend this to 3 or more classes. So that's with one reference pattern. You can see that if I'm using more than one reference pattern, we will get a piecewise linear surface along this area between A and C B and C and A and B. So these are straight lines. They can be piecewise linear with multi-reference patterns, and the decision surfaces can become quite complicated. Right. Practical limitations. Supposing I am using pictures and I'm converting the pictures directly to vectors by using each pixel value as an element of the vector. Supposing the pictures are 512 by 512 bits, pixels. And supposing the resolution is 8 bits per pixel, which would be grey pictures. If it's color, it would be 24 bits, but color would introduce a real problem with the distance classifier, because if you interpret the 24 bits as a vector, or an element of a vector, then as you increase the 24-bit value from all noughts, which would be total black, to all white, which would be all ones on the 24 bits. As you go through, there are discontinuities between the R, G, and B. The picture, which is very red and nothing else, maximum red, the next value up would be red going to 0, and no, start with the least significant end, starting with the green, no, the blue, RGB. Counting up on 24 bits, you will get to a position where you've got maximum blue, which would be, I'll draw it as 2 bits, it would be 0, 0, 1, 1, sorry, 0, 0, 1, 1, this is R, G, and B. Then if I'm incrementing this, which would increment the distance, the next value would be 0, 0, 0, 1, 0, 0. And that is a huge perceptual difference in the actual pixel value, because here we've gone from RGB, maximum blue, 1 increment up takes us to 0 blue and introducing green. So there are non-linearities in the color image. So we're not dealing with color, we're dealing with black and white, grey. So that is not a problem to consider right now. But if you're using these, color does introduce non-linearities in the distance. Right, now what's gone wrong? Right, carrying on. Right, the practical limitations. Our pictures are 512 by 512. We have 8 bits resolution per pixel, i.e. per element. Ah! Come back. Oh. Right, I've got it back now. Right, so there's the resolution. Let's have 50 classes.
Oh,
Got it back, yes.
Wow, this is good.
And let's take 100 reference patterns per class. Quite a lot of data has to be processed to do the distance classification. Right, how much exactly? Remember, we are calculating the summation I equals 1 to the total resolution is now going to be 512 by 512 squared, which is, I think, 256,000. And AI minus BI squared We've got a subtraction, which is the same as addition in terms of processing time, but we've got the squaring operation, which is a multiplication. And from your assembly language knowledge of level 1 and level 2, you know multiplication takes a series of instructions. It's much longer to implement. It's a shift and add process, 8 bits resolution. It will take a lot longer than the simple addition. Right, so let's work out how many calculations we've got to do. How many multiplications? We've got, first of all, 50 classes and 100 reference patterns per class, so that is 5,000 distances to measure, which is quite significant. Now, for each distance, the number of operations, because we've got 250,000 pixels, it is going to be 250,000 summations. So for the summation, it is going to be, oh, go away, erase. Two, 5, 6 instructions. Now for the that's the summation of the summation here. We've got a subtraction there, so the subtraction there is the same as summation. It's going to be another 256,000 instructions. And now the multiplication will involve, for 8 bits, it's going to be a shift, so there'll be 8 instructions and an add. It's going to be 16 instructions done 250,000 times, so the squaring is going to be something like 16 times 256,000 instructions. So if we add this up, it's going to be 16, something like 18, let's call it 20. Times 256,000. It is going to be, what's that? It's going to be about 5 million instructions. Now, for 5 million instructions, if your computer is 2.3 gigs, it is going to take a few milliseconds. But let's go back. We had 50 classes and we had 100 reference patterns per class. Now that might be okay for sorting out a relatively small problem, but if one wanted to recognize, say, all Brunel University students face-wise, then instead of 50 classes, we'd have 10,000. And maybe we need 1,000 reference patterns per class for reliability, because we don't want inseparability problems. These figures could be very much larger in practical applications. If we multiply a few milliseconds by 1,000, increasing the size of the problem, it becomes slow. Now, technology is ever increasing. We're down to 5 nanoseconds feature size now on electronics. It is going away, but it's still a problem. And as we increase the size and the resolution of these recognition tasks, the processing time can be a problem. What is the answer? And the answer is don't use Euclidean distance. It is too computer hungry in terms of processing. So the next topic I want to look at is approximate distances. And the first approximate distance I want to look at is called the city block distance. If you're working in America, it's often called the Manhattan distance. That is the first distance. There is an alternative called the square distance. Now, I'll give you the last thing I want to leave you with today, because we're about to run out of time, is the equation for the city block. I'll call it DCB. It is the summation I equals 1 to D, the same as the Euclidean. That summation is in the Euclidean distance, but the relationship between the elements, we do not use the squared operation. We have AI minus BI, and instead of squaring it, we simply take the modulus. We're therefore eliminating the multiplication, and that will go 10, 20, maybe 100 times faster than the Euclidean distance. And so there is the equation, and work I want you to do before the next lecture is whoops. There is pattern A, and I want the contour of distance 1. All the patterns that using this equation are a distance 1 from the reference pattern A. Now I'll give you the Euclidean distance. I'll draw that on as carefully as I can. The Euclidean distance is going to be a circle, radius 1. That is the Euclidean. Now you find the contour of equidistance for the city block using that equation there. Okay, guys, that's all I've got time for today. Thanks for listening. I think the technology has been a little bit better this week than last Monday. We'll try and improve even further next week. Any questions, get in touch or email me or contact me via chat. Bye for now.
Thank you. Bye.